Welcome to the course Control of Mobile Robots. My name is Magnus Egerstedt and I'm a professor at Georgia Tech in the School of Electrical and Computer Engineering, and I am delighted to be able to deliver this course to you. The focus of the course is how do you make mobile robots move in effective and safe and predictable ways, meaning that they don't slam into obstacles, they move smoothly and nicely without having weird oscillations in their motions. And the trick to achieving this is something called control theory. And this first module of the course is going to focus on controls and control theory and what it is and what the pieces are that you need to be able to actually control robots. Before I dive in, though, I wanted to say a few words about myself. My research hammer is control theory. So that, as I've already said, deals with how do you make things move or behave well. And this could be stock markets, this could be cruise controllers, this could be limiting the spread of epidemics, for instance, using vaccination strategies. So control theory doesn't really have a tight, necessary coupling to robotics. It's a general language for describing how things behave. Now, if that's my hammer, my nail is robotics. And I'm very, very interested in how do you make robots do elegant and useful things. And in my lab, we do really three different types of robotics. One is swarm robotics. So how do you get lots and lots of robots to do exciting things together? The other is something called behavior-based control or behavior-based robotics. And we will see quite a bit of this in this course. A behavior is basically a controller that's in charge of something like going towards a landmark or not slamming into obstacles or following corridors or things like that. And the question is, how do you design these behaviors and how do you patch them together? A third thing that I'm interested in is field robotics, meaning how do you take robots and put them out in the unstructured, strange world outside of the lab, meaning if you have a robot driving through the forest, all of a sudden there are no corridors or hallways or doors and life becomes much more complicated. So before we start, I want to show a little video that came out of my lab a few years ago. So here, this is an example of swarm robotics. We have 15 robots that have been asked to spell GRITS. And GRITS stands for Georgia Robotics and Intelligence Systems. That's the robotics lab that I'm directing. And these robots have to figure out where they should go in the letter. They need to figure out how they should go there. And they need to figure out how to go there without slamming into each other. So what's going on there is control design at multiple levels of abstraction. One is the high level, where should you go? Then you have the lower level, which deals with, okay, I know where I want to be. How do I actually get there without driving into other robots, for instance? And as you can see, these robots with very limited information, meaning they don't really know where every other robot is, they figure out where they should go in this formation. And this video I like for multiple reasons. One is because there's a lot of control theory going on underneath the hood. And the second is you will be able to do this at the end of this course. So let's talk a little bit about the course. Control theory will play a key role, meaning how do you actually control systems? And this will be done decoupled from robotics. But then we're going to couple in the robotic applications by looking at robot models, because not all robots are the same. Some are hopping, some are slithering, some are rolling, some are flying, and different type of robots require different type of controllers. We're going to look in general at mobility, meaning how do you make the robots move? That's the main question we're interested in this course. And then we'll end with applications. So what can you actually use these robots for, and where do we need the kinds of solutions that we'll be going through in the course? I do want to say, though, that the course is not about artificial intelligence, which is the high-level planning, meaning what should the robots actually be doing? We're going to be dealing with the question of, well, they have already figured out what they should be doing. How should they be doing it? We're not going to deal much with perception, meaning how do we take computer vision data and actually turn it into something actable? Or how do we actually design perception algorithms? We're going to assume that someone else has done this, and we're going to act on the perceptual data that we already have. And it's not a mechanical engineering course, meaning we're not going to be building robots or dealing with different kinds of robotic designs. However, there is a slight little caveat to that, because we will indeed be looking at some hardware aspects of robotics. Here is a video from a course I taught on campus at Georgia Tech. And this is a robot that's running a lot of the things that we're learning in this course, meaning it's figuring out how to get to a landmark, in this case, a purple little tape mark on the floor, but it has to do it while avoiding obstacles. So it has to design different controllers for different situations. For instance, the left robot is not doing so well. The right robot here is doing even worse. It's slamming into things. But the point is that at the end of this course, you will be able to do this, hopefully better than what we're seeing right now, because the robots are all over the place. Here we're seeing some other instantiations of this. See how the robot is oscillating a little bit too much, but it is able to navigate the cardboard box. And, well, the right robot is driving into chairs. The other robot seems to be a little confused. So these are examples of robotic controllers that aren't perfectly tuned and perfectly designed. Let's look at the final race, where we're going to see what the outcome would be if you've done the control design properly. See, they're going straight. There's very little oscillation. Well, one robot is oscillating, but the purple robot there seems to be doing really well, going quite straight. And this, in my mind, is a successful robotic control design. So, what is actually in the course, or how is it structured? Well, we're going to have lectures. They're going to be 8 mini lectures each week, and they're going to be 7 weeks in total. Each week will be capped by a quiz. And there will also be glue lectures, so lectures that are designed to glue what I do in my slides to the actual quizzes. And then, as a bonus, there will be additional material. This is not mandatory, but if you do it, your experience will no doubt be more enjoyable. First of all, we have a robotic simulator that we use in the lab called SimIam. It runs on MATLAB, and this will be part of the course, meaning you can do it if you want to. Few words, MATLAB is the programming environment we're using because this is one of the standards in the engineering world. Now, you will be able to get MATLAB for free as a student license through this course. So this will come at no extra cost to you. But then we'll also map this onto a real hardware platform where, if you're interested, you build your own robot. Because I truly believe that there's nothing more exciting than doing the theory right and then seeing things move in the real world. So, if you follow along the course, do the simulation, and also build the robot, at the end, you will have an awesome platform that can actually run around in the world without slamming into things. Before we do this, though, I want to make one minor, or maybe even major, disclaimer. To do robotics right, and to do control theory right, there is no way around the fact that you need math. So mathematics will play a key role. And this may be a little uncomfortable to some of you at first, but we're doing it for a reason. And I will try my best to make sure that I explain why we're actually going through all the stuff that we're going through. But things like linear algebra, matrices, and eigenvalues will show up. Differential equations will play a key role. Calculus, derivatives, and integrals will be everywhere. And this is just something you have to do in order to be able to do robotics right. And I hope you will be following me along this ride for this 7-week adventure. As a final note, before the actual course begins, let me take this opportunity to introduce the team behind the course. They are all graduate students in robotics and control theory here at Georgia Tech. And here is Smriti Chopra. Smriti is going to be running the glue lectures. So these are lectures that are going to map the general stuff that I do in class onto the particulars of the weekly quizzes. And Smriti is also going to be highly involved on the discussion forums. And here we have JP Delacroix. JP is going to be the master of ceremony when it comes to running the robotic experiments that we're sprinkling in throughout the course to highlight and stress particular key points. And JP is also the key force behind the optional simulation part of the course, and he will be running the weekly programming assignments. And here, lastly, is Roland O'Flaherty. And Roland is the hardware guy. He is going to show us how to build robots. And this will also be an optional weekly feature where we will be building platforms that at the end of the day we can implement and run our controllers and code on. And Roland tells me that he is actually going to produce a cooking show, but instead of baking bread, we will be baking robots.